All right, folks, we are once again coming at you live from the Venditto Haven of Peace, Love, and Physics, and I will show you how to do a couple more homework questions, numbers 34 and 38. All right, we will start with 34, which talks about a balloon, a really, really big balloon. It's 226 kgs. It has a volume of 325 cubic meters. That's a big balloon. It happens to be in air, in the atmosphere, which is 1.29 kilograms per cubic meter. It also tells you the density of the helium that is inside that balloon, 0.179 kilograms per cubic meter. So you can see helium is less than not quite, a little more than 1/10 the density of air. But again, just because they give you a number doesn't mean you're going to use it. In fact, in this particular problem, you won't even need the density of He. So hopefully, when you see that balloon, you can identify two arrows acting on it, a buoyant force pushing it up and gravity pulling it down. And so that's part A. Just draw the arrows, draw the forces, okay? All right, part B says it wants to know what is the buoyant force acting on that balloon, which you know is rho GV. Just remember, it's the density of the air, the fluid that is pushing out of the way. All right, so it's density of the air, which is again the mass divided by volume, whatever, but it gives you that number 1.29. If you take its mass divided by volume and multiply it by volume, you're left with its just plain old mass. So remember, buoyancy is the weight of the fluid you displace. So a density times a volume, you're left with mass times g. So a force is mg, and g is an acceleration, g. So the density of air was given right there. It's 1.29, and that's kilograms per cubic meter. G is 9.8, and the volume that is submerged under the fluid is the volume of the whole thing. You know that's 325. So multiply 1.29 by 9.8 by 325. You'll get 4,108.65. We don't need that many digits. We're only given 3 anywho, so we will keep 3. 4,110 newtons is the buoyant force acting on that balloon. So the up arrow, 4,110 newtons. All right, and then part C wants us to figure out what is the net force on that balloon. What is it? Does everything add up to something? And that's what we're going to find out. What does it all add up to? So sum of the forces in the y equals ma in the y. In this case, we don't need to call it ma. We can just call it the net force, F net. So the sum of the forces in the y is the net force. The sum of the forces means add them all together. In this case, adding them together, we clearly subtract because buoyancy is up, gravity is down. That's the net force. So the buoyant force is what we just figured out. It's 4,108.65, or if you round it, it's 4,110, doesn't matter. From that, we will subtract Fg, the force of gravity on this object, which again is 226 kgs, but then we need to multiply that by 9.8. So Fb is what we got over here. When you do the math, I can leave all of those digits in, or if the answer is still in your calculator, all then you'll have to do is subtract from that number 226 times 9.8 in parentheses. So this answer is probably still in your calculator. From that, just push the minus button. It will be answer minus, put it in parentheses, 226 times 9.8. That will get you this, 1,893.65. Again, we don't need that many digits. We're only given 3 in the first place, so 1890, huh? Not a bad year. All right, and then part D says how much weight would we, or how much mass, I'm sorry, would we need to add to this balloon? So tie a bunch of mass to the string here and make it add up to my life. Absolutely nothing. So how much mass would we have to add to that balloon to get that net force equal to 0? So if the net force is nothing, then there's still only two forces. buoyancy and gravity. I mean, it's still those same two forces, buoyancy minus gravity. Only difference is in this case, it will add up to the number of push-ups I've done today, which means then buoyancy is equal to gravity. All right, buoyancy is equal to gravity. Buoyancy is what we just got way up there. Remember, that's 4,108.65 or 4,110. Will be equal to gravity. Now, what's the force of gravity? It is the mass of the whole entire thing times g. It's mg. So there's two parts to the mass of the whole entire thing. There's the mass of the balloon itself plus the mass we are going to add to it. That net mass, or what I jokingly again call the mass hole, that's the mass of the whole thing, times g is the force of gravity. So what I'm going to do is isolate that mad, which is the additional mass. I'm going to just divide it by g, so this will be an FB divided by g. Once you divide by g, that makes these parentheses unnecessaries, which means then FB minus, or this quantity subtracted over FB over g now, minus the mass of the balloon itself, will be the amount of mad, or the additional mass I can add to make it add up to nothing. So remember, that buoyant force, 4,110, is what I would call it. If you want to use the actual, 4108.65, you can, but 41,110, I'm going to divide that by 9.8. So there's your FB divided by G. From that, I'm going to subtract the mass of the balloon, which was given at the beginning, 226 kgs. That's the additional mass that I can add, and it turns out 193 kgs is what it would take to add to that balloon to make it add up to nothing, to make it so that it won't rise, it won't fall, it'll just be there in the air. All right. 38 deals with the one in the book that looks just like this. So there's an object hanging from a spring scale, and it's just in air. There's nothing else really special over there. So an object hanging from a scale, and it tells you what the scale reads. Then you take that same object with the same spring scale, same string, whatever, but dunk it underwater, and the spring scale will read something differently, and you would say, wow, apparently it weighs something different, which, again, that term is one hopefully you remember, apparent weight. It just means the weight registered by an object when it is submerged in a fluid, and its apparent weight is, in fact, the force of tension. All right, so what I did is I said, okay, in air, it tells you that the tension force is 5 newtons. All right, if it's just hanging there in air on a string, 5 newtons. So if it's just hanging there in air, then how many arrows do you see? And that's 2, just tension and gravity. All right. So then in this case, gravity is mg. Well, in any case, Fg is mg. So the mass of this object is its force due to gravity divided by the acceleration due to gravity. So force is mass times acceleration, which means mass is simply force divided by acceleration. The force of gravity divided by 9.8. So 5 newtons divided by 9.8 meters per second kilogram, or meters per second squared, gives you 0.51 kg. So the mass of this object is 0.51 kgs. All right. The goal of question 38 is to see what the density of this object is. So that's what you want to row. Okay. What is the density? And remember, the density doesn't change whether it's submerged in water or floating in air. It doesn't matter. That density will stay the same. So our goal is a density of that object, which means, gosh, we're halfway there. Someone should write a song. That means we have the mass. The last thing we need is just volume. So how do we get the volume of that guy? When you're submerged in water, hopefully you can see 3 arrows now. There is a tension and gravity, the same 2 we had before, but once you're submerged in water, there is a much more prevalent buoyant force pushing upwards. And all three of those will again add up to the number of squat thrusts I did today, which is absolutely none. So it's a buoyancy plus tension, which is that apparent weight now, that's the tension, minus gravity is 0. So the buoyant force is just gravity minus tension. All right? Gravity it's given is 5 newtons. The tension when it is submerged in water is also given is 3.5 newtons. So 5 minus 3.5, that's not too tough. That's 1.5. All right, so the buoyant force is simply 5 minus 3.5. It's 1.5 newtons. Okay, now the buoyant force, again, remember, is the rho of the liquid times whatever planet you're on times the volume that is submerged. All right, that's what any given buoyant force is the density of the liquid that is submerged in times the acceleration due to gravity on whatever planet you're hanging out on times the volume of the object that is submerged. It is in fact the entire object that is submerged. So that V sub is the V of the object. That equals 1.5 newtons because we just said the buoyant force is 1.5 newtons up there. So the volume in this case is 1.5 newtons divided by the density liquid times G, which is 1,000 kilograms per cubic meter times 9.8 meters per second squared. All right, so the volume again is that divided by rho G. Rho is 1,000, 9.8. All right, so this this denominator is so darn big that the fact that this is 9.8 instead of 10 really doesn't matter. We're taking 1.5 and dividing it by 10,000. All right, so it's 1/10,000th of 1.5. So all this becomes is 1.5 times 10 to the negative 4th cubic meters. That's all it is, 1.5 times 10. So that number didn't even change, just times 10 to the negative 4th cubic meters. So there's the other halfway of the there that we needed, because the density of any object is its mass divided by its volume. All right, its mass we got earlier, we said it was 0.51 kgs. We got that from that chain of logic right there. Its volume 1.5 e negative 4 cubic meters. We got that from above there. Push the divide button, you will get 3,330 kilograms per cubic meter. So it's considerably denser than water. And that strategery is one way that I think is very kind of, I call it baby stepping your way through it. It's where you take one step to figure out its mass, take another step to figure out its volume, or another step to figure out the buoyant force, then I don't know, a third step to figure out its volume, and a fourth step to figure out the density of the object. All right, so it's a very step-intensive strategery. There's another way we can do it, which would be a tad more sophisticated, but that would be if you start with the goal and then solve everything with letters, which is something that I want us all to really work on, is letters rather than numbers. What that means is over here, you see where I have an FG is equal to MG, M then is FG over G. So I rearranged letters and didn't put numbers in until I did the math. And what I'm going to do is the same thing, but over here, this mass, I'm going to replace it with, instead of the number 0.51, I'm going to replace it with the letters that number is made of. So it's not made of 5 divided by 9.8, it's made of FG divided by G. All right, it's made of FG divided by G. That's what M is equal to. So where this M is, I am going to replace it with FG divided by G. That is M, and then I'm going to divide that by the volume. What is the volume? The volume, you know, is 1.5 times 10 to the negative 4th, but what is that number made of? All right, that number is made up of 1.5 newtons divided by 1,000 times 9.8. okay? But what is 1,000 is the density of the liquid. 9.8 is the acceleration due to gravity. So this is rho of the liquid. This 9.8 is g. All right, so I'm just going to, instead of using numbers, I'm going to keep the letters. Rho g. The numerator for V is the 1.5 newtons. It's the buoyant force. And how do we figure out the buoyant force? We took Fg minus Ft. All right? Fg, the force of gravity, minus the force of tension. So Fg minus Ft is the buoyant force. That buoyant force then divided by rho g is how we spell the letter V. All right? So this V is going to be the buoyant force, which was Fg minus Ft divided by rho g. And what I'm going to do is put that term over here where this volume is in the denominator. So I'm going to have a complex fraction. It's going to be Fg minus Ft over rho times g. All right? So the density of this object is this quantity, which is its mass, divided by this quantity, which is its volume. If complex fractions are too complex, remember whenever you divide by a fraction, you can flip it and multiply. So it'll be Fg rho g divided by g Fg minus Ft. All right, but what we can honestly now do is start just putting numbers in place here, because this Fg, we said earlier, it was given in the problem, when it's resting in air, or when it's hanging there in air, the Fg is 5 newtons. So this Fg is 5.0 newtons. I'm going to divide that by g again, which is 9.8 meters per second squared. So there's the numerator. There's the main division bar right there. And now I'm going to take Fg again minus Ft. That Fg, we said already, is 5.0 newtons. From that I'm going to subtract 3.5 newtons, because that was the tension when it was submerged in water. Okay, so there's this same numerator right there, Fg minus Ft. That's where the 1.5 came from. Fg minus Ft, that up there is where the number 1.5 came from. So all I did was put those there, and then I'm going to divide it by what we divided by over here, the rho times g. So this is going to be 1,000 times 9.8. All right, now when you do this math, what I would do is use parentheses. All right, use parentheses. So do the math all at once, meaning open a parentheses before you push the number 5. So then take 5 and divide it by 9.8, then close the parenthesis. So now you're done telling the calculator what you want your main numerator to be. It's just 5 divided by 9.8. Push the divide button. You want the denominator to be that whole entire quantity. So what you're going to need to do is not that, because of that minus sign. So you're going to need to open a second parenthesis there, then close that internal parenthesis there. Then you're going to have to put this in one parenthesis and then finally close that. So these two outer ones are what tell the calculator it's this entire thing is our denominator. It's made up of 2 items, this quantity divided by that quantity. All right? So when it says solve with letters, what that means is make it look like this. Put letters in place, have the letters dance. Don't put numbers in until the end, and try doing the math all at once. And it's a decent thing to practice. You'll end up with the exact same number, 3,330 kilograms per cubic meter. But again, just a skill to please start practicing a little bit is they call it symbolically solve, which just means use letters instead of numbers. And then hopefully this example means, well, gosh, all that number is just made up of these letters. So just keep the letters in and don't put numbers in until the end. All right, so let the letters dance. Let the letters dance. And yay! Physics in the summer time. There's a video of you watching a video of you watching a video of you. I think the matrix is in there somewhere. All right. Bye.